so far at this point, we derived the formulas for the Fourier series given a function. So we have formulas, we can calculate the coefficients of the Fourier series. Yeah. All right. So that's the general, this is the general formula. But later we consider two special cases corresponding to f even function and odd function. Yeah. So for even function, we have a simplified version of the formula. For the odd function, we have another simplified formula. So that's what we are doing at this point. Yeah. Also, we have another basic result. That is the convergence result. Yeah. So here, let me repeat that result again. Yeah. Because this is an infinite series. When we calculate infinite series, we need to consider if this series is convergent or not. Yeah. All right. Yeah. But our result is, it is convergent, the infinite series. When the function f, so here we need to consider the properties of this function f. When the function is continuous, then it is convergent at any point that is continuous. So the function is continuous at that point. Yeah. So that's the first part. Second part, when the function is not continuous, so we consider individual discontinuity points. Yeah. So let's use one isolated discontinuity point. At that point, it is also convergent. This function is also convergent, but it converges to the point, the average of the left limit and the right limit of that continuous function. Left limit and the right limit. Okay? All right. Yeah. So here you can see, so one important assumption we need to use here, that is, so here, so let me just, this information I didn't talk about last time. So let me explain this special case this time. Yeah. So now we're talking about the, convergence question. Okay, convergence, and we look at the discontinuity. Okay, one discontinuity. Let's say x equals x0. Okay, so at this point, f function is discontinuous. All right. Regarding the discontinuity, let's recall in calculus, what do we mean? A function is not continuous at one particular point. Let's recall a little bit. So last time I didn't, dig in very deep at this point. So now let's look at a little more. Discontinuity. Here, at this point, there is a, we consider this case. Left limit approaches from the left side. So we use that negative. Okay, left limit and the right limit. So we need to look at these two limits. for at each discontinuity point. Yeah. And we need these two limits exists, right? Exist. These two, left limit, right limit, both exist. Yeah. But there is a possibility one of the two limits may not exist, right? Yeah, may not exist. Yeah, that could happen, right? Yeah, so let me draw a simple graph here. Yeah. For example, suppose this is the discontinuity point, x0. Okay, all right. Then, from the left-hand side, the function, when it's close to, the limit does not exist. Okay? Fluctuation up and down, so that's one. Another possibility is, the function, goes to infinity. Yeah. It does not exist. All right? Yeah. Okay? Yeah. So, one of the two limits may not exist, right? That could happen when we talk about discontinuity, continuity points of a function. Yeah. So for our convergence situation, all right, in order to get our infinite Fourier series convergent, we need both limits exist. Otherwise, we cannot get a convergence result. Okay? Yeah. So both exists. Yeah. Then we know it converges to the average of these two limits. Yeah. It converges to the average of these two limits. So we need to assume that. We need to assume that regarding discontinuity. Yeah. Yeah. So that's why we, this time we understand a little more details. Okay? Yeah. And in calculus, actually, there is another concept regarding discontinuity. There is a concept called a removable discontinuity. Non-removable and removable discontinuity. Right? Yeah. So related to that. So what's that removable discontinuity? The discontinuity can be removed. Yeah, so we call it removable. Yeah, so let me give you that meaning. Yeah. So for a function, yeah, we consider one discontinuity at this point. Yeah. You have left limit, right limit, right? Yeah. So the function, left limit and the right limit, all right? Left limit and right limit are the same. Okay? But at this x0 point, the function value is different. Jump. All right? Yeah? The function value, yeah, because at this point, so not here. The function value is here. Yeah. In this case, we call this is a removable discontinuity. Yeah. Why? Because it can be removed. Let's redefine the function value, not original value. Let's redefine it as the limit. All right? Define the function value to be the limit, left limit, right limit. So this discontinuity we call the removable. Yeah. This discontinuity removable. Removable discontinuity. All right? Yeah. Non-removable, so here, the non-removable case, yeah. So x0, left limit exists, right limit also exists, right? Yeah. This kind of discontinuity is non-removable. Yeah. Because in this case, both limits exist, but they are different. Different, no matter how you define the function value at this point, still not continuous. Right. So you can redefine it, okay, in any value, but you can never make it continuous. So that's the non-removable discontinuity. Yeah. So for our Fourier series, the convergence, yeah, so we can handle this case. Non-removable discontinuity we can handle. Okay? Yeah. So no problem. We do not require the the discontinuity removable. Yeah. We do not require it. Yeah. So non-removable discontinuity, the Fourier series still convergent. Yeah. So that's my further explanation for this topic, convergence topic. Okay, yeah. So give you better understanding, general understanding. All right, so that's what we did last time. Now let's move to the new part. Yeah. Yeah. So part C, the remaining, yeah. I mean here just copy the formulas. Nothing new on this slide. Yeah. Even function, odd function, cosine series, sine series. Yeah. All right. Next, we need to do some examples. Yeah. So let's work on some examples. The first one, triangle and half-range extension. Yeah. So here, something new. Here is the half-range extension. Yeah. A special operation. Yeah. We commonly use when we expand a given function in its Fourier series. Yeah. So we have some freedom. Yeah. So we can do a half-range extension. Yeah. Let me explain the idea here. All right. F function. So here, a part of the f, yeah, so f function is given in this shape, triangle shape. All right. Yeah. On the interval between 0 and the capital L. Yeah. So only in this period we have the shape of this function. Outside this shape, yeah, no other information. Yeah, no other information. Yeah. All right. But now, remember, when we expand this function in its Fourier series, we need to create a periodic function, right? Yeah. So this is not a periodic function. Okay? Yeah. This is not a periodic function. So we need to do extension to make a valid periodic function. Then we can do the Fourier series expansion. Yeah. So the first step, we need to extend it as a periodic function, but when we do it, there are different ways to do it. Yeah. So it's not a unique way. Yeah. We have many different ways to do the periodic extension. Yeah. So here, from the phrase here, half-range extension. Yeah. So the function given is in a half range. Yeah. From 0 to L, yeah, this half is given. Yeah. Yeah. Because in our previous setting, when we consider the general periodic, so we consider 2L periodic, right? periodic. Okay. 2 pi periodic function, 2L, right? Yeah. So we have the other half from negative L to L. This negative half we do not have. Yeah. So we need to extend it. So we need to find a convenient way to fill it in, fill that negative half in to get a, whole 2L period. Yeah. But when we make it up, the negative half, we have freedom to choose which way we want to use. Yeah. All right. So most of the time, people use. So this is the, if we use formulas. Yeah. So that's the formula of f function. Yeah. So linear function. Yeah, here. Yeah. I hope you can see the meaning of this function, piecewise function. The peak is at L over 2. The peak. Yeah. From 0 to L over 2, it's a linear function, increasing linear function. Then from L over 2 to L, decreasing linear function. Yeah. All right. So then, but when we do extension, there are 2 commonly used ways to do it. The first one is even extension. Second one is odd extension. So what's that even? From the name, you can guess easily. Even extension. After extension, we get an even function. Yeah. So we do the, reflection. Mirror. Yeah. Put a mirror here. We do reflection. Yeah. That's an even extension. Yeah. After extension, we get an even function. Okay. Odd extension. Yeah. So do the symmetric operation with respect to the origin. Symmetric. Yeah. All right. Yeah. So after extension, you get an odd function. Yeah. So these 2 different half-range extensions, are the most commonly used ways we can do the extension. All right. Now, let's calculate the Fourier series formula for these 2 half-range extensions. Yeah. The first one, even periodic extension. Yeah. It's an even function, so we need to use the even Fourier formula, even function formula. Yeah. And a 2 pi periodic. So other places, so we do the periodic extension. Yeah. In one period, yeah. So we have an even function. Yeah. All right. So we need to use this Fourier cosine series to calculate the coefficients, the formula. Right. Yeah. So the specific formula. Yeah. So let's do the calculation. Okay. Yeah. So integral calculation. A0 an. Yeah. Yeah. All right. Yeah. So after that, let's write our Fourier series. All right. Yeah. Explicitly, yeah, like this. Okay. All right. Yeah. So you get so for the f function, yeah. So this f function 2 pi periodic. Okay. Yeah. So you have the Fourier cosine series representation. Yeah. It's a continuous function, so yeah, it's convergent. So you plug in the function value everywhere. Yeah. So both sides the same, and the infinite series convergent to the function value. Yeah. So you can write a equality. Yeah. Any point you plug in, so you get it. Equality. Yeah. All right. Let's do the second one. Then we compare a little bit. These two different representations. Yeah. The first one we use the cosine Fourier formulas. Second, we use the sine version of Fourier formulas. Yeah. All right. So same thing, but this time the extension, we do the odd extension. Okay. Yeah. You know, following the definition of odd function. Yeah. Then 2 pi periodic. 2L periodic extension on the whole real axis. Right. Yeah. So now let's apply the Fourier sine series formula. Yeah. Yeah. Let's do the calculation. Yeah. Bn. Yeah. So the integral. Yeah. So we get this one, and we can write f function in the sine Fourier sine series form. Yeah. All right. So the same function. Yeah. Here. Yeah. Let's think about it. Yeah. For the same function, in the interval from 0 to L. That's same function, right? Yeah. Other intervals different. Yeah. So the same function we mean here, the original given same function, but only on a portion of the real axis. Yeah. Same, but when we do different extension, so the final Fourier series have completely 2 different forms. Yeah. All right. So now, I like to put the cosine Fourier cosine series. Yeah. So these 2 formulas, these 2 completely different formulas, right? Yeah. But in this interval from between 0 and L, between these this interval, on this interval, these 2 series have the same value, right? Yeah? Yeah. Using 2 different ways, but the final value is the same. Yeah. All right. But in other different intervals, so sometimes they are the same, sometimes they are different. Yeah. 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 So here you can see the comments. Yeah. Yeah. If we do not use Fourier series, yeah, we cannot see the results like this, right? Yeah? Yeah. Yeah. One sine series, another cosine series, yeah? So they can have the same value, yeah, everywhere in this interval, yeah? Yeah. So we can plug in, for example, so here, yeah, if I take L over 2, yeah, this point, L over 2, this same point, I can plug into the first formula and also second formula, and they must be the same. The function values must be the same. Okay? Yeah? That's non-trivial, right? Yeah, because it's hard to see it. Yeah. Yeah. And hard to prove it, right? Yeah. Yeah. If you do not use the Fourier series expansion, yeah, it's hard. Hard to see it. Yeah. 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 Something interesting. Yeah. All right. Yeah, let me see if that is the end. Yeah, could be. Yeah. Oh, yeah. So when I see this symbol, yeah, that's the end. All right. now I can jump to the part D. All right. Fourier integral topic. Okay, all right. D.1, Fourier series in approximation theory. Yeah, so approximation, yeah, we need to do some work, do some study in approximation theory, yeah? Because in the real world application, actually most of the time, we need to use approximation to solve the problem. Yeah. It's hard to get an exact value. Yeah. Most of the time, it's very hard to get exact value. Yeah. So we need to do a lot of approximation. Yeah. So now, we want to see because Fourier series is an infinite series. Infinite series, so there is an approximation issue. That is, because think about, when you calculate infinite series, solving real world problems, you cannot use infinite terms, right? You have to use finite terms. You can only use finite terms. Nobody can use infinitely many terms. When the series is relatively complicated, if the series is very easy, then you can use infinite terms, right? Yeah. For example, as easy as, yeah, this, my pen is there. For example, the infinite series is very simple, like 1 plus 1/2 plus 1/4, right? Yeah. For this kind of, we can calculate the accurate result, including all the infinite terms. But for the general infinite series, you cannot do that. Yeah. So we have to use approximation. Yeah. So here, let's understand this topic. Approximate a function by partial sum. Yeah? You only take the first few terms, partial sum. We call it partial sum. Okay, all right. Yeah. So consider this function. Yeah. And yeah. Remember we did last time, right? Yeah. Actually, we calculated the first 3 partial sum. S1, yeah, the first partial sum. S2, second partial sum. And S3, the third partial sum. So you can see we get a better and a better approximation. So now we want to study how to control the error. But because when you do approximation, there is an error term, right? Yeah. How large is the error? We want to control that error. If you do not know how large is your approximation error, that it's not good enough, right? Because you cannot control the error. Yeah. All right. So let's look at how to control the error. Yeah. All right. So that function we did last time. Okay. All right. So this time we study. Yeah. So we use nth partial sum. Yeah. This is n partial sum. So capital N. Yeah. So we only take the first few terms like this. Yeah. We know approximately. Yeah. The equal is approximately equal. Yeah. All right. But we want to study how large is the error. Yeah, there is a difference. Yeah, how large is that difference? Yeah. All right. Yeah. So now we want to, so this time, let's consider how to do the approximation. All right, Consider all the trigonometric polynomials of the same degree n of the form. So here. So we want to, so the current question, so how good is this approximation? So you see the question here, but our general consideration is like this. General consideration. All right. Is this approximation the best approximation or not? All right? Best approximation among, because when you talk about best approximation, you need to specify the general form, right? The general form is the nth order trigonometric polynomials. Degree n. Degree n. All right. Order degree. Degree n. Trigonometric polynomials. Right? So here. So among all the degree n trigonometric polynomials, is this one, the one we truncated, our partial sum of the Fourier series, partial sum. Is that partial sum is the best approximation or not? Can we find, other trigonometric degree n trigonometric polynomials, such that the approximation to the original function is better? Now, we want to think about this question. All right? Better means the error smaller, right? The error part, the smaller, the better. All right. So let's compare the error part. All right. So we consider all the possible degree n trigonometric polynomials. All the possible, that means, so you have freedom to change these coefficients. You do not have to use little a0, little an, little bn. So the general case, we use capital. Okay, capital A0, capital An, capital Bn. Those capital coefficients, they are not coming from Fourier coefficients. They are not necessary Fourier arbitrary coefficients. Capital, when you see the capital letters, that means they could be arbitrary coefficients. Little a0, we mean the Fourier coefficients. So we want to see among all the possible capital A, capital B coefficients, which one is the best? Which one gives us the best approximation to the original f function? That's the question we want to study here. All right. Where is my remote control? I'll put some here. All right. So next, so capital version, right? So do not get confused. Arbitrary coefficients. So all right. So different. All right. Then which one has the best approximation? Next we study. We want to understand this. I didn't. All right. Meaning of the best approximation. So we want to use some nice formula to describe the error part. Well, we want to talk about the error part. Okay, all right. Yeah. Yeah. All right. Yeah. So we compare. Yeah. We compare the degree n trigonometric polynomials. Yeah. All right. Yeah. Yeah. The Fourier series, partial sum of the Fourier series, the first one, the general. Yeah. So that the second, that's the general degree n trigonometric polynomials. All right. The best means the error of the approximation is as small as possible. So now we need to calculate the error part. Yeah. All right. Error. So how to represent error? All right. Yeah. So little f function. Yeah. Partial sum function. Yeah. Oh, actually, this f is original. Original function. Yeah. Little f function. That's also, yeah, not the partial sum. Yeah. Yeah. Partial sum. We need to use a different notation. All right. So the little f function, that's original. So then capital F function. Yeah. So that's the arbitrary function in the trigonometric polynomial of degree n, and we treat all such functions as in a space. It is a space of function, linear space. So all those functions, we put them together. Yeah. So it forms a linear space. Yeah. Okay. Now, so in that linear space, we want to pick one function that has the best approximation. The best approximation means this error part. How do we get? Yeah. So the maximum value of the difference, difference between the original function and any of the trigonometric function with degree n. That maximum is minimum. That's the error. That's we can say that's one way to represent error. One way. Because there are many different ways. When we define the error, there are many different ways to define the error part. Yeah. So this way, this is one of the several popular ways to define the error. Yeah. All right. The first way. Yeah. We have other ways. All right. But this way you can see we draw the graph. So we draw the graph. Yeah. Yeah. So the solid lines, you know, corresponding to the original function, right? Yeah. So the original function has a discontinuity. The capital F function must be continuous function, right? Yeah. Trigonometric function of degree n, it's a continuous function. So this dashed line, the graph of the dashed line, yeah. So it's a continuous function. Yeah. Little f, you know, there is a discontinuity at x0 point. Yeah. Here you can see, if we use this error definition, yeah. So here we want to show that this error definition is not good here. Okay? Yeah. So you can see the error difference. Yeah. Yeah. The error difference for this part, the approximation is not very good, right? You know? Yeah. It's very hard to get a very good approximation in this discontinuity point. Yeah. At continuity points, approximation, yeah, very good. Okay, but at this discontinuity point, the approximation not very good. All right. Then we define another. Yeah, because people have freedom to define error term, right? Yeah, people have freedom. Yeah. So another. Yeah, because after we observed, this part, approximation, not very good. Yeah. So then another definition. We take the difference, then we square, yeah, because when we look at the errors, positive, negative, we don't want positive, negative to cancel out, right? Yeah. Positive, negative, so we want to accumulate positive, negative error. We don't want them to cancel out. Then 0, that means no error, right? So we don't want positive error, negative error cancel out. Then 0, no error. That's not correct, right? So for that reason, here we use absolute value to, remove the negative error case, negative value. Yeah. So always positive. This place we use square to remove the negative case. Yeah. All right. Then we take integral, yeah, the difference square, then we take integral. Yeah. So you know the geometric meaning of integral, right? What's the geometric meaning of integral? Okay? The area, right? Yeah. So here. Yeah. All right. Here, I try to interpret the meaning of this error definition. Okay. All right. So here, we have a certain interval between negative pi and pi. Yeah. So we want to do approximation. Okay, all right. Yeah. And one function on this one function is discontinuous. All right, yeah, like this, because we need to consider the discontinuity things. All right. Yeah. Another function, approximation, trigonometric, like that. Okay? Yeah. All right. Yeah. So you take difference. All right. Take difference, then square, then the integral. So we calculate. Yeah. So if we draw the error, yeah, the difference. The square of difference. Yeah. So the square difference should be small, right? Yeah. Yeah. The square of the difference should be small, right? Yeah. All right. Yeah. Then we calculate this integral. That means the area under the square of difference. We use square error of f. All right. So now you see. Yeah. So here, accumulated. So here, the error. Square of error accumulated in this interval. We define this error. And this definition of the error is much better than the first one. Much better than the first one. Okay? Yeah? All right. So why it's better? One way it is better is when we do calculation, the second error is more friendly than the first error. Why? Because the first error, you have absolute value. You use the absolute value function. Then when you take the derivative, it's hard, right? Yeah, absolute value, derivative. There are a lot of places you cannot find a derivative, right? Also, you need to look at the different intervals. That's not convenient. But the second way, when we calculate derivative, very easy, right? Yeah, square. Yeah, so very friendly. Yeah. So now let's use the second definition of the error. We want to study the best approximation question. All right. So estimate the error, this E. Let's calculate this E with this formula. Yeah. So we calculate this E, the integral. Yeah. Yeah. So there are 3 integral terms. Let's do the calculation. Okay. All right. Yeah. There, here we need to use the orthogonality property. Yeah. So these formulas, so that's the orthogonality formulas, right? Yeah. 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 So there are these orthogonality formulas. Yeah. Yeah. We want to use these orthogonality formulas to simplify this error expression. Yeah. Yeah. Orthogonality, it's a lot of terms because a lot of zeros. Yeah. The cross terms, right? Especially. Yeah. So when you do multiplication, there are many cross terms. Yeah? All zero. Okay? All right. Now, minimum square error theorem, the final result. Yeah. Let me show you the final result. Yeah. All right. So the approximation. So here. Yeah. Yeah. So we have, Fourier, partial sum of the Fourier series. Then, the general trigonometric function of degree n. All right. Then we calculate that capital E. Yeah. All right. There are 3 integrals. Let's calculate one by one. 3 integrals. Yeah. The first one, yeah, like that. Yeah. First one. Then all the cross terms all gone. Okay. Yeah. So the only, so the sine function, cosine function, integral with itself non-zero, right? Yeah. So you can see, the sum of squares. That's the result. The first integral. Second integral. Yeah. Second integral. Yeah. So all the cross terms gone. So only the same function. Yeah. That one remain. Yeah. So you have that expression. Then the third one. Oh, yeah. Yes. Yeah. So now let's calculate E. All right. E. Yeah. So you use that result there. All right. Yeah. And the E star. So here. Yeah. So here. We define, so we want to, so what's E? We want E star. So E star, so we consider E star. E star, we make capital AN the same as little an. Capital BN, we make it little bn. That's the E star. So we want to compare the general E and that special E star. And which one is larger, which one is smaller. Yeah. General E, we have freedom to choose, right? But the one special selection, we capital A, capital B, we use the Fourier series coefficients. Then we compare. All right? Yeah. Let's take a 10-something minute.